right, now we're actually ready to start talking about calculus. So hopefully you're feeling pretty comfortable with rules of algebra, that sort of thing, logarithms. If you need to brush up on stuff like trigonometry, don't hesitate to reach out or use the resources I've posted so you can catch up on that stuff. But now we're actually ready to talk about what's actually calculus. Now, you'll see what I've got written up here. It might not be the first thing that if people remember when they get to the other side of a calculus course. If someone asks them, "What did you learn in that class?" This might not be the first thing that pops into their head, but it turns out pretty much everything you're going to learn how to do in a calculus course, it ends up building back on this notion in some way, shape, or form. So let's go ahead and dig into what it means when we talk about a function's limit. So the typical notation we're going to write for something like this. So you'll recall we'll have our function f of x, and if we're talking about a limit for a function, it's a very what you would call a local property. It's the sort of thing where we're looking at what's happening as we let x get, as you said, this arrow indicates x is getting close to some specific x coordinate. I just used c as a placeholder, and we might say that the limiting value of our function, or the limit of f of x, as we let x get close to c, is equal to some number L. So what that ends up meaning, I've kind of already let the cat out of the bag. So that remember, f of x, that's as you say, for any given value of x, that's going to give you a number back, the function's value, right? So the idea here is that we can guarantee that our values for f of x stay close in some sense. So again, note the quotes there. That's often sort of math teacher, code for this is kind of technical and I don't want to, bog you down too much in it. I'm sort of standing between you and the true rigorous mathematical definition here. But the idea is f of x, we can guarantee that it stays close enough to L if we keep our independent variable values, our x coordinates, so to speak, if we make sure that x stays close enough to c, then f of x also has to stay close, enough to L in some sense. As I said, if you really want to dig into this, section 1.2 in our textbook talks about what this definition means in a very precise sense. For our purposes, dealing with it in this kind of intuitive structure is going to be sufficient for what needs to happen in Calculus 1. All right, so that's our notation. Like I said, I would read this as the limit of f of x as x approaches c is equal to some number L. So that's our notation. So we're going to take a look at this and all of the different ways a function might be handed to us. But for now, we're actually going to punt on the one that's kind of the most common, that being looking at a function as given to us by a formula. So in this first section of material, and the actual calculus book proper, we're going to be looking at what limits mean in the context of a function that comes to us via either a graph or via a table of values. So hang on just a sec. I need to clear this off so I can mess around with an example. All right, this is a pretty good example, relatively basic. Hopefully this isn't going to catch anybody flat-footed in terms of what's going on here. I just grabbed our standard quadratic function, f of x equals x squared. Its graph, hopefully this doesn't surprise you, is kind of the standard parabola opening upwards, the happy parabola as I often describe it. And we've got that in place. If you want to, feel free to generate this with your favorite graphing device, but it's not necessary for what we're doing. So what I want to take a look at is what this function is doing in a limiting sense as we let x get close to, in this instance, 0. Maybe that's not 100% legible on the screen. There we go. That looks a bit more like a 0. All right. So you can kind of tell what's going on here. Remember, in graphical terms, f of x corresponds to our y coordinates of the points that live on this graph, right? So the way I usually describe this is imagine you're a bug, or I like bug, but what have you. And you're walking along a wire that's kind of in the shape of this graph. Don't ask me why the wire is drooping like that. Anyway, so imagine you're a bug and you're walking down toward this point with an x coordinate of 0. What are your y coordinates doing as your little bug legs carry you down here? So the height's going down, 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 and it ends up getting closer and closer and closer the more and more we kind of slink in on this, getting close to 0. So, and you'll notice it doesn't make a difference whether we as the bug start over here or if we start from over on the other side. No matter where we begin on the wire, if we're coming in towards 0, both of, these are both ends of the wire leading us toward a y coordinate 0 when it's all said and done. So we would say the limit of this particular function as we let x get close to 0 is also 0. Spoilers, that's not always what happens, but it works well for this example. So hopefully that makes sense. So we're going to play around with this in a couple of other, situations. So I'm going to make an adjustment to this function. So pay very close attention because when this comes back from the other side of the awful jump cut, hopefully you'll be able to notice the difference. Okay, so I've maneuvered things just a little bit. You notice the difference? Yeah, so there's this big hole sitting right here at the origin where our quadratic was passing through. I kind of redefined my function so that x equals 0, we have a function value of 1. So note the little quotation marks around the equals right there. I should have been more specific with like a piecewise thing, but I'm short on board space, so bear with me. Anywho, so for this new f of x, does the limit as we approach 0 change? Yes, no. Feel free to pause, think about it or whatever, and Okay, so as it turns out, the answer in this instance is no, it actually doesn't matter. If you go back to my idea of the bug, so our bug walking along through here, does the bug, he just keeps on walking. What are my y coordinates doing as I get close to 0? So that's kind of the big difference here. We're not concerned about what's happening right at 0. We want to know what's happening as we get close to it. So our bug is still hopping down to 0. The bug would have no way of knowing that it's supposed to teleport up to this 1 that's up here. Now, technically, yeah, the wire shouldn't still be hanging like this, but suspend disbelief for a bit, okay? Again, same deal over on this side. As our bug walks close to this, it's always closing in on 0. It doesn't know about this jump right here. So as it turns out, that limiting value is still 0. As it turns out, it doesn't even matter if the function is defined at all right there. I could just eradicate that in its entirety. We just have the quadratic with like a hole in it. So you could technically imagine this as like x cubed over x if you want to play around with it algebraically. That's the x squared quadratic anywhere except at 0 where we've got this hole in the graph. Same thing, same principle. X equals, as you said, the limiting value as x gets close to 0 is still 0. So that can be kind of it's a kind of a big deal. A lot of what you've done in mathematics courses up till now probably relied on what was happening at exact values, what's happening at 0 or at 1 or at 42, what have you. In this instance, we don't actually care that much about what's happening right at the point. We care what's happening as we get close to the point. I really apologize for the jump cuts. I personally hate them in videos, but you don't want to watch me just erase a board repeatedly. So, sort of a moral of the story here as far as limiting behavior is concerned is what's happening at the point precisely isn't really the meat of what's going on with the limit. What's happening close to x equals c as we close in on it, like I said, is kind of the big, it was the big jump that ended up making a lot of stuff that drives calculus and, surprisingly enough, a lot of other modern mathematics. That was a big deal at the time for someone to make that transition thought. If you're looking for sort of a real-world context for this, I like to describe this when it comes to limits. So imagine you're reading a book, like old school, paper book. I was going to get one, but I didn't have one that matched the type of book I was going to talk about. So you have these two characters you're reading along in the book. They're having this really heated conversation. It's like both characters seem like they're really on the edge. And you get to the bottom of the page, and you hear one, as you say, the author describes one of the characters as feeling for the grip in his holster or something like that. Then you're all ready to turn to the next page, and it turns out that somebody ripped it out of your book. Those jerks. So, the next page is missing. The next page you get to is actually the start of the next chapter, and it's describing police officers investigating a crime scene and talking about a body lying on the floor. So, you don't technically have the exact page of the book because it was, taken away or destroyed or what have you. But you can tell from what's going on what most likely happened on that page, right? Somebody probably got shot. So that's kind of an idea here. So try to think about it in terms of real world examples. I've had students grab at all kinds of stuff through the years. I used to do an example where I would actually walk headfirst into a wall. So if that gives you a chuckle, good. That was kind of why I did it. But anyway, so that's the idea here. Thinking about what's happening as we get close to a point, not worrying about what's happening right at it. All right, so we'll keep playing around with some examples here. I think I'm going to transition to looking at what's happening with the table of values, and then we'll come back to talking about graphs some more. So stay tuned.